every star that dies will actually turn into a black hole. A black hole is really reserved for more massive stars. It does not matter what the black hole is made out of. The only thing that matters is mass, spin, and charge. So, what is a supermassive black hole, besides an awesome song by Muse? They are the supermassive black holes that you see at the center of galaxies. And yes, the Milky Way has one. It's called Seeger A star, and it's located in the Sagittarius constellation. Just one more reason why Sagittarius is objectively the best constellation. A note on the masses of these different categories. A stellar mass black hole is typically around 5 to 12 solar masses, and a solar mass is one sun, right? So we say a solar mass is one of our suns. So if we say we have a black hole that has 12 solar masses, what we're saying is it's got 12 times the material than the sun. That's what we're saying. 12 solar masses, 12 times more massive than the sun. Now, you can go online and you can find these lists, and people will say, oh, well, stellar mass black hole is anything between 1 and 100 solar masses. And the reality is, we have never found a black hole that's 1 solar mass, and we've never found a black hole that is 100 solar masses. Most black holes are sitting above 5 solar masses and below 20 solar masses. That's the range for most stellar mass black holes that we find. If you find a black hole that's 30 solar masses, that's a really large stellar mass black hole. Again, you'll go and you'll read these magazines and it'll be like, scientists define this, blah, blah, blah. Again, it depends on who you ask. But very typically, because humans love rounded numbers, they will say 1 to 100 or 10 to 100. And the reality is, you know, most black holes do not get that high and they never get that low. So just be aware of that. So most stellar mass black holes are sitting around 5 times to 20 times the mass of our sun. But then we jump to supermassive black holes. And supermassive black holes are truly, amazingly, ridiculously enormous. Most supermassive black holes are in the millions of solar mass range, right? Millions of times as massive as the sun. And some of them are in the billions of times, or thousands of millions of times more massive than the sun. These are truly supermassive objects, and they are at the center of galaxies. So if you want to check out some galaxies that have truly massive, supermassive black holes at their centers, I hope you're near the Constellation Virgo. So Messier objects 60, 84, and 87 are all galaxies that house supermassive black holes that are billions of times more massive than our sun. Messier 84, for example, houses a supermassive black hole that's 1.5 billion solar masses. 1.5 billion times as massive as the sun. Messier 60 has a supermassive black hole that's 4.5 billion times the mass of our sun. The point I'm trying to get at is that they're called supermassive for a reason. So these things are just enormously, ridiculously, incomprehensibly big. And the crazy thing is that there's nothing in between. Think about that for a minute. There's almost nothing in the hard sciences that does this. Science a lot of times deals with fuzzy sets. Things that don't have a solid category and a solid category, and never the twain shall meet. Where do you put your duck-billed platypus and all that good stuff? And this is an enormous problem in astronomy. We want to categorize things. We want to say this is an asteroid, and this is a comet, and this is a planet, and this is not a planet. When is a planet really a dwarf planet? At what point does a planet have enough atmosphere to be considered a gas planet? When is a brown dwarf a star? It's all well and good to say you're a star when you can burn hydrogen, but what about objects that burn just deuterium? It's all well and good to say this is an asteroid and this is a comet, but what about objects that exhibit equal characteristics of a comet and an asteroid? And that's the problem in astronomy that we see all the time. And yet, with black holes, it's the opposite problem. Over in this category, we have several solar masses. And over in this category, we have millions or billions of solar masses. And that's insane. And it's fine to pick an arbitrary line for black holes and say this is your category and this is your category, but it turns out the categories are not even sort of close to each other. They're so far apart that you have to start wondering at some point, what's in between? Where are the objects that are 100 solar masses, or 2,000 solar masses, or 10,000 solar masses? Where are these objects? And if your brain has been going, wait, where's all the stuff in between this whole time? You're not alone. There's actually a lot of astronomers that have tried to solve this question for a really long time. First of all, there's not a whole lot of candidates out there for intermediate mass black holes. But of the candidates that are out there, the detection methods can have pretty large ranges of margins of error. So there's intrinsic uncertainty in pretty much every detection method for everything, and it's important to remember that those margins of error matter. It's also important to remember that margins of error happen for a reason. Space is really big and no detection is perfect. It's not like scientists are out there using substandard detection methods. It's inherent in the job. For example, what Pasham's research did was look at a black hole that's in M82, which is 12 million light years away. Studying anything that's 12 million light years away is difficult. That would be like sitting on the moon and watching a Game of Thrones episode being played on a smartphone in San Francisco and accurately predicting who's gonna die next. It's difficult! Pasham and his team, they didn't actually discover this black hole. This black hole was already known in the M82 galaxy. What they did is they took it from the "we think this is an intermediate black hole" camp, and they put it in the "we're pretty darn sure that this is an intermediate black hole" camp. And that's actually a very difficult camp to get into. So this black hole, because it's an M82, is creatively called M82X1. That's the name of the black hole. So what Pasham did is he actually went back through years of data from the Rossi X-ray Timing Explorer, and he was looking for very, very specific ratios of frequency oscillations that would actually tell him how massive this black hole was. And what he got out of that was 428 solar masses plus or minus 105 solar masses. So 428 solar masses minus 105 solar masses plus 105 solar masses still solidly puts it in an intermediate black hole range. So again, this particular black hole was not discovered 2 months ago. What it was it was solidly placed into a "we are pretty darn sure the intermediate mass black holes exist and there is one here" camp. And that is just, that's really an enormous step in the right direction. And that's not going to sound as cool as a headline, "Astronomer discovers new type of black hole," but the reality is all of this stuff, all of these discoveries happen in phases. So 60 years ago, astronomers weren't even sure that black holes existed. And now there's so much evidence that they do. But we're really getting to a point where we can look at types of black holes, specifically intermediate mass black holes, and that's the frontier for us today, for our generation. So we're looking at these objects, we don't know where they come from, but we can see this evidence piling up that they really exist and that there's something to them, and it's very, very exciting. Thank you so much for watching this episode. If you have questions or comments, leave them in the comment section, and join me next week when I will be talking about how black holes are portrayed in the media and how stupid Hollywood is. So I'm gonna make an analogy that's gonna be useless but awesome. Mass, spin, and charge. Oh my gosh, that was so bad. It's like couple solar masses, billions of solar masses.